Okay, second video. Before I go any further, let's quickly talk about some things, some notation, some terminology that will be brought up in metabolism. The first thing I want to point out is this set of arrows that you see right here, where there's one on the top and one on the bottom, and they both have a single head. This is used to show a reaction in general, but the way that I will use them in my videos is to show a reversible reaction, also known as a fast step. Okay, the way that I will generally show irreversible or slow step reactions is with these sort of unequal arrows to show that yes, the reaction can go in the other direction, but it's really being driven this way, downwards, by the energetics from reactants to products. When I say that it's being driven by the energetics, what it means is that this compound is much, much lower in energy than this compound. So the energetics, the entropy, enthalpy, it's all driving the reaction this way. Okay. Other notation that you might see, this will come up in metabolism, it will also come up in cell biology, so I think it's important to know in general. You'll see this notation. It's basically the stem of an arrow, but then it has a flat head instead of having the arrowhead. This means inhibits. Okay, it will usually be drawn to show that it inhibits an enzyme, it inhibits a particular reaction. The opposite of inhibits would be activates, which is this one stem with this normal looking arrowhead, okay, and that means activates, and that's the opposite of inhibits. I realize that my notation is a little confusing for this step between fructose 1,6-biphosphate and phosphoenol pyruvate, because I use this double-headed arrow. But what I just wanted to illustrate there is that this is a number of fast, reversible steps that were not really that important to show. And I'm just using this notation because of the small amount of space that I have on my whiteboard, so I apologize for that confusion. Sort of other things to think about in metabolism, because we use a lot of terminology that has a particular meaning in the vernacular when we're just speaking out loud, and it has a very, very different and specific, precise meaning when it comes to biology or metabolism. So you've probably heard me mention reversible and irreversible reactions. Reversible means that the energetics of the substrate and the product are relatively equal. Okay, so that means that reversible reactions exist relatively near equilibrium. There's not much more product, there's not much more substrate, and the reaction is generally going back and forth at approximately the same rate. Okay, when I say irreversible reactions, that means biologically or functionally irreversible. You know, they're not irreversible in a vacuum. Those steps in glycolysis are going to be with the enzymes hexokinase, phosphofructokinase, and pyruvate kinase. Okay, and what that means is that the substrate is at an energetically higher point, much, much higher than the product. And so the energetics, as I said, will be driven mainly towards the products, unless some sort of modification occurs with the enzyme in order to drive the reaction backwards. So these irreversible steps are also referred to as the slow steps or the rate-limiting steps. Those are synonymous. Whereas reversible reactions are considered fast reactions. This is important because if you can sort of think about metabolism like traffic, a traffic jam, or a grid system, you know, in the middle of London. So let's say that these different pathways, okay, you have glycolysis to the citric acid cycle, but then you also have fatty acids coming off of here, you have ketone bodies, and then from here you have glycogen synthesis, and you also have breakdown of glycogenolysis. The lysis at the end just means that you're breaking down glycogen. So those branches off, you can think of as intersections, like you would find in central London. So the point that I'm trying to make with all of this is that the irreversible or rate-limiting reactions are going to be the ones that are regulated hormonally by insulin and glucagon, because there's no sense in speeding up the already fast reactions if you want to get metabolism to go faster or to go in a different direction. So imagine that you're driving along from point A to point B and you have to go over a bridge, okay? And the lanes go from 2 lanes to 1 lane as you're going over that bridge. Now, that bridge is probably always going to have a traffic jam, right? That's sort of like our slow step, or in this case, 3 slow steps in metabolism, i.e., if that traffic jam is there, it doesn't matter how fast the rest of your route takes you. You're still going to arrive at your destination probably within a couple of minutes, regardless of how fast you went for the rest of the journey. But if that traffic jam suddenly becomes worse, it's going to tack a lot of time onto your travel time, right? And if it suddenly goes away, then you'll get to your destination a lot quicker than you previously expected. This is how irreversible, slow, rate-limiting steps work in metabolism. So if you can't speed up these slow steps, you're not going to speed up the overall process. And that's the importance of having these irreversible steps, because these are your control points in metabolism. And when you have hormonal release of insulin or glucagon in response to something happening in the environment, those hormones are going to be acting on these enzymes in order to control what a particular cell is doing with its energy source, whether it's conserving it or whether it's spending it.